Okay. So last class we have discussed about the instantaneous sampling, and we have seen different spectrums for Fs greater than 2 Fm, Fs is equals to 2 Fm, and Fs less than 2 Fm. Okay. This particular case is called as Nyquist rate. Okay, this is called as oversampling. Then, and the last one, it is called under sampling, which is not allowable. Which is not allowable means if you do the sampling which is less than 2 Fm, the overlapping of the spectrums will come into picture, and while recovering we cannot extract the original modulating signal. Okay, so once again I am discussing it with respect to some spectrums so that it will be more clear for you. Now, whenever the term signal recovery will come, that means we need to recover the original modulating signal M of t from the S of t. S of t is called as sample signal. Okay, sample signal, and it will pass through a low pass filter whose response is h of f, or you can say h of t, and then the output must be the message signal, or you can say it is a continuous time signal. Okay, and this is called as your sample signal. Now last class we have discussed about instantaneous sampling. So if it is instantaneous sampling, we are getting some sort of spectrum regarding these particular cases. Now how to extract it? Now let us consider the filter response is, last class I have written directly as omega n, but you can write as omega c minus omega c, and this is h of omega, this is omega, and this is minus omega. Okay, and this is 0. Now when the sample signals is crossing through this filter, we will get our modulating signal. So here I will write m of t is equals to s of t convolution with h of t. Then, so if I will take the Fourier transform s of m of omega, this I can write as s of omega. Convolution property of a Fourier transform is simple multiplication with h of omega. So with the help of this relation, I can extract the modulating signal. Now we will see how we can extract the data. So first of all, I am discussing with this oversampling case. Now case 1. Okay, so step by step we will see. If Fs is greater than 2 Fm. Now whenever this Fs is greater than 2 Fm, how my spectrum look like? My spectrums are, this is having 0 to, this is omega m minus omega m, this is omega s, this is 2 omega s dot 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 up to infinite. Similarly, left hand side also I can represent minus omega s, and here also I can represent minus 2 omega s dot 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 minus omega. So this is my s of omega, sample signal. Now in this case, when it is Fs greater than 2 Fm, or you can say omega s greater than 2 omega m, there will be a small gap between two consecutive spectrums. Now what is this? Last class also we have discussed that this particular bandwidth is called as guard band. Okay. So when this guard will come into picture, this is omega s plus omega m, and this is omega s minus omega m. This guard band will come into picture when your omega s minus omega m is greater than omega m, and it satisfies omega s is greater than 2 omega m, what we have considered here. Done? Now for this particular case, when it is entered to this low pass filter, our filter response is varies from minus omega c to omega c. Now in this case, let us consider omega c is equals to omega m, because my motive is to extract the message component, which is a band limited signal, and I am setting this omega c as omega m and this minus omega c as omega m. This is the criteria. So when this particular sample is crossing through this particular filter, my output response will look like this. So output is m of omega, this is omega m, this is, first of all it will identify omega c at minus omega c, where omega c is omega m and minus omega c is minus omega m, and having certain amplitude. So that means the filter response identifies the band limited signal of omega c is equals to omega m. Omega c is the filter response. If it is equal to omega m, that means it can easily extract the data. This is for which case? For fs greater than 2 fm case. Similarly, case 2, if fs is equals to 2 fm, if fs is equals to 2 fm means it is a Nyquist criterion, in which my sample signals will just touch the starting point of one, act as a end point of another spectrum, like this, and dot dot dot. So this is minus omega, this is plus omega, this is s of omega, here this is omega m, this is minus omega m, this is 0, this particular point is omega s, this is 2 omega s, this is minus omega s, and this is minus 2 omega s. Now in this case what happens? You can see at this particular point I can write omega s plus omega m, okay, which is same as 2 omega s minus omega m. Or in this particular side I can write omega s minus omega m. So what it indicates? It indicates that omega s minus omega m is equals to omega m. So omega s is equals to twice omega s. So that means it satisfies your Nyquist criterion, because the limitation for both the points are same. So if this is the case, then when this sample is passed through this filter, and this filter response is omega c and omega minus omega c, and if it is matched to omega c is equals to omega m. Now in this case what happens? If omega, first I am considering omega c is equals to omega m, what happens? Okay. So if the filter response omega c is equals to omega m, that means it will extract this particular band limited signal. So here I can say up to this much minus omega to omega m, the information can be recovered. So that means it indicates what? If it is satisfied oversampling, it can extract the modulating signal. If it is a band limited to omega c and omega m, if it is Nyquist rate also, the information can be extracted without considering the next part, because the end points are touches with the another one, so it will only extract the modulating signal. So this is the second case. And the third case is what? If Fs is less than 2 FM, intersecting points will be identified by these spectrums, and the filter extraction may not be same as our modulating signal. It is an addition of some other part also. Some other part of this and some other part of this particular spectrum. Okay. So this is about when our filter response omega c is equals to omega m, so that we can extract the information. Okay. Okay. Now these are the three special cases. Basically, in exam we used to ask on this particular relation. So first case is if my filter response, omega c is called as a filter response. So let me erase it. So here you can see, first this is the filter response. If the filter response is equal to omega s minus omega m, then what will happen? Then omega c is less than omega m, what will happen? And omega c greater than omega s minus omega m, what will happen? Okay. Now let us consider we have done the sampling with the help of oversampling which satisfies the criteria Fs greater than 2Fn. Now this sample is fed to the filter and we need to extract modulating signal from the sample, received sample signal, in which the filter response is h of t. Now this filter response is having the band limitation omega c and minus omega c. So this is h of omega. Okay, and its condition is what? Its condition is h of omega is equals to 1 mod omega less than omega c and 0 otherwise. So this is the response. Mod omega c means plus omega minus omega c, so maximum value is 1. Done. Now when the sample is entered to this, and here there are special cases arising. If omega c is equals to omega s minus omega m, if this is the response, can we extract the modulating signal? That is the question. So we will see. So let us consider this particular field. So sample signal, only two samples I am considering. This is first sample, this is the second sample, and this is the reflection of a particular sample. It is minus omega s, this is omega s, dot dot dot, this is also, this is s of omega, this is 0, this is omega m, minus omega m, and this is omega s minus omega m, this is omega s plus omega m, and with a certain amplitude. Then I have considered only these three. So this is the part. Now when this particular sample is feeding in this, now the omega c is omega s minus omega m. Now here, first case, omega c is equals to omega s minus omega m. Now if omega c is this and this is also minus omega s plus omega m for left hand side, done. So what will be my response? My response means the filter response is this much. Okay, filter response is this much, because omega s minus omega m is equals to omega c. So this is for positive part and this is the reflection part. Now if this is the criteria, then also we can extract the modulating signal without any interference. You can see there is a guard band, there is no information. In there is a bandwidth, there is no information. So output of the filter will look like this. So this is the m of omega m and minus omega m with amplitude 1. This is m of omega, because here the filter amplitude is 1 we have considered. So whatever the amplitude of s of omega, same amplitude will reflect here with multiplication of 1. But the thing is what? Up to how much bandwidth it is considering. So it is considering up to this much. Guard band is there, my information is also recovered without any losses. So that means in this case we can extract our modulating signal. Next we will see if my omega c is less than omega m, what happens. So this is the first special case. Now the second case is, again consider some sample. So this is the sample signal s of omega, this is omega m. This is one more sample centered at omega s. This is one more sample and minus omega s. This is minus omega m. Okay. Now here the filter characteristics. The filter characteristics is omega c is less than omega m. So that means your filter response will look like this. It is less than. So this is our less than. This line indicates this is omega c and this is minus omega c. So when the sample is entering to this particular filter whose response is less than omega m, you are going to lose the information. Only this much information you will identify. This much. That is omega c minus omega m, and this is the m of omega we are extracting. Now what is this? Rest of the information we have lost. This much information we have lost. So if the informations are lost, the energy is also lost. If the energy is lost, that means we cannot recover the original message signal. So this dotted line we cannot recover because the filter response is less than your band limited signal. So this is also one case. Practically we are not using it because we need to extract the original modulating signal, though this is the analogy. Okay. Now next case, as I have written, this is the second case, this is the first case, this is second case, and the third case is case 3. If omega c is greater than omega s minus omega m, then what will happen? Let's see. So it is the same figure. So case 3, omega c greater than omega s minus omega m. So now in this figure you can see this is omega s minus omega m. Your omega s is greater than this. So that means this much amount it can take to this much. Let us consider. So this is your omega c. Similarly, for the reflection part also, we can consider it is minus omega c. So when this sort of sample is passed through this filter response, whose omega c is greater than omega s minus omega m, the output will look like this. So this is a band limited signal, but there will be some other informations are going to be added which act as a noise. Okay. So this is up to this much. So this is m of omega. This is my information, okay, modulating signal, but additional informations are there. Additional information means it acts as noise, which will deteriorate your message signal, and we cannot recover the original message component. So this case is also not allowed for practical case. This is not allowed. Similarly, here we are missing our information. So this case is also not allowed for practical usage. Maximum we can go for this case. Omega c is equals to omega s minus omega n, and one more, omega c is equals to omega n. So we need to design our filter with respect to these two cases. If you are designing your filter with respect to second case and third case, then definitely we are going to lose our message signal. We cannot recover the original message component from the sampled signal what it is received at the receiver end. Okay. So now we are going to discuss about the natural sampling. Now natural sampling itself indicates that there is a variation in the amplitude of a sample naturally. Now in this case there is a switch, okay, and in this switch is controlled by pulses which I will feed here, and this pulse is a rectangular pulse, and the time period is Ts. That means from here to here the time period is Ts. And here I will provide the modulating signal, and at the output I will get the sample signal. Done. Now this is the clock signal, or you can say it is called pulse train, whose time period is Ts, and this Ts is nothing but sampling time period, which is equals to 1 by Fs, 1 by 2 Fm, and this Fs if is equals to twice of F. So modulating signal is having angular frequency omega n, which we can represent in terms of F. If it is a single tone, if it is a multi-tone, then your Fs is equals to twice of F max of F1, F2, F3. How many number of frequencies available in our modulating signal or message signal. So now this particular switch, or you can say it is called sampler, which is controlled by the clock pulses whose time period is Ts, and this Ts is decided by the Nyquist rate with the help of input modulating signal. Now let me draw the figures first, then we will analyze. So this is my modulating signal M of T. Okay. Then I am considering the pulse train. This is the pulse train. This is the pulse train. You can write this one C of T, or you can write it is P of T, any of these ones. Like this. So this is 0, this is Ts, this is 2Ts, midpoint is 3Ts, this is minus Ts, this is minus 2Ts, dot dot dot, and having amplitude 1. And the pulse is having a pulse width of tau. This is tau. Okay. Now when you feed these two to the mixer or to a multiplier, output will be our natural sample signal. Now natural sample signal means, here you can see this is my modulating signal, this is the sample variation, this is the sample variation. So this is M of N T S. Okay. So these are the pulses with slight amplitude variation, like this pulse will come. Amplitude variation. In enlarged method, I am representing it like this. The pulse top is not flat, it is some variation is there. So this is called as our natural sampling. But the natural sampling, if it is followed by a quantization, then we can get the discrete value. But in instantaneous, what happens, since we have considered in instantaneous as a impulse train, so directly we are getting the discrete positions with discrete values. But since it is a sampling, natural sampling, here number of samples we are obtaining at a regular time interval of Ts, but the amplitude varies. Okay. So if this is the case, then if it is followed by a quantization, then you can obtain, if this signal is provided to the quantizer, okay, if it is provided to the quantizer, we can obtain the discrete values like this. So these are the discrete values. Here I will write M of N. This is N position. This is 0. This is Ts. This is 2Ts. This is 3Ts. 4Ts, 5Ts, this is minus Ts, minus 2Ts. So when we are using the instantaneous sampling, here there is an impulse train multiplied with your modulating signal or your continuous signal, directly we are getting the discrete values. But in natural sampling and flat top sampling, it doesn't happen, because here we have considered the pulses. Pulse is having, it is nothing but a rectangular function. Okay, so this pulse train we have used as in a particular switch condition. If the switch is on and off for a regular time interval for a time period of Ts, we are getting this sort of sample, and the samples are in this particular manner. Samples are available, but the amplitudes are varying. So it is called as a natural sample. Now this natural sample value, if it is fit to the quantizer, we will get our discrete signal. But in instantaneous, what happens? Impulse train multiplied with modulating signal, directly we are getting the discrete values. Okay, this is the basic difference. Now we will analyze these pulses. Now we will analyze step by step the mathematical analysis of this modulating signal, how it is convoluted into your pulse chain, and how we are getting the sample signal in time domain as well as in frequency domain. Now the samples are like this. Okay, if it is an impulse train, we are getting the uniform amplitude for each and every spectrum. Now since it is a sample signal, we will not get the output of a sample with a uniform amplitude. It will form as a different amplitude for different position. You can see for Ts amplitude is different, 2Ts amplitude is different, 3Ts amplitude is different, 4Ts amplitude is different. So for different amplitude, your different potential will be available to it, and we will get the different spectrum. And since we are using the rectangular function, here again if we take a Fourier transform of this rectangular, it will become as a sinc function. So we need to analyze that sinc function also. Okay, so it is having certain derivation. Let me write it. Okay. So for mathematical analysis, we need some assumption. So what are the assumptions? First, as you can see in this figure, it is a continuous, it is a pulse train, rectangular train having certain amplitude 1, or you can consider A also, which is repeated at a regular interval of time Ts. Okay, let us consider 1 plus, and it is a periodic signal. So if it is a periodic signal, you need to analyze with respect to the Fourier series. So whenever this Fourier series will come into picture, you need to identify the coefficient of that particular signal. What are the coefficients? As we have written in our signal system Fourier series part, in which we have to identify certain relations. If f of t is a periodic sequence, I can represent this as a naught plus summation n is equals to minus infinity to infinity. It is a n cos n omega naught t plus b n sin n omega naught t, like this. So this is the Fourier series expansion. Okay, and this Fourier series expansion, a naught is called as our DC component, which is 1 by t 0 to t f of t into dt. Similarly, what is an? An is equals to 2 by t 0 to t f of t cos n omega naught t into dt. Similarly, what is bn? Bn is equals to 2 by t 0 to t f of t sin n omega naught t. So this is the cases arises when f of t is a periodic signal. Now in that periodic signal, the two cases are there. First, if it is even or not, or it is odd signal. Okay, if the periodic sequence is an even and symmetric in nature, then you can determine a naught and a n not equals to 0, as well as a naught is not equals to 0, but b n will be 0. Since it is symmetric, it is an even component, and cos term is with respect to a n, so a n will exist. Similarly, if it is odd, a naught will exist, a n is equals to 0, and b n may exist, may not exist. That is for odd signal. Okay. So this is the basic concept behind the representation of this particular pulse. It is a periodic pulse repeated at a regular interval of time with the same amplitude. That means it satisfies the periodicity property. What is the periodicity property? X of t is equals to x of t plus capital T. So if this property is satisfied, that means that signal is called as a periodic signal. Okay. Using this assumption, come to this side. So first, there are two signals are there. One is your continuous signal, one is your pulse train, or you can write as a C of t. Let us consider P of t or C of t is a periodic signal. Now if it is a periodic signal, we need to identify the coefficient so that the relation will multiply with respect to the message component, and we can form as a output message sample signal, which can be analyzed in terms of Fourier spectrums or in terms of frequency domain. Now how to represent it? First, since it is satisfying the periodicity, C of t is equals to C of t plus t naught. Here t naught is nothing but sampling time period. Okay, and omega naught is nothing but omega s, which is equals to 2 pi by ds. Okay, this is the assumption. Now if it is periodic signal, Either you can go for the trigonometric expansion or you can go for the exponential expansion, any of these. Here I am using the exponential expansion because anyway we are identifying the discrete positions. So here C of t k minus infinite to infinite a suffix k e to the power j omega naught k into t into dt. So this is only this much, not dt. When you take this integral, it will look like this. So when this integral comes to left hand side, it becomes an integration divided by 1 by t naught minus t naught by 2 t naught by 2 c of t. This exponential which is plus on the right hand side, when it is come to the next left hand side, it will become e to the power minus omega naught kt into dt. Now this is the coefficient we need to identify. After determination of this coefficient, substitute here, multiply with m of t, you will get your sample signal. That is the simple analysis. But before identifying this ak, first you need to analyze the pulse. Which particular pulse we are going to take. Now since this is our particular pulse, I have considered here, whose amplitude is a, time period is ts. Ts means minus ts by 2 to plus ts by 2. So this particular part you can write ts by 2 and this particular part you can write minus ts by 2. Here I have written t naught, you can write ts. Okay. So within this particular pulse, how much DC component is present? That is the constant coefficient. You can say as what is the constant coefficient of this pulse. How we are going to identify? Ak 1 by t naught total time period minus t naught by 2 t naught 2. What is the function c of t? Here it is a c of t. What is the c of t amplitude? Amplitude is a. E to the power minus j omega naught k t into dt. It is a simple integration. Integrate it. If you integrate e to the power minus j omega naught k t divided by minus j omega naught k, you will get. And the time period is minus ts by 2 ts by 2 and a by ts, because t naught is nothing but a sampling time period. So I have substituted here. Take this value outside. Take this minus inside. Put this limitation. You will get a divided by j omega naught k into ts whole into e to the power j omega naught k ts by 2 minus e to the power minus j omega naught k by 2. Okay. Now when I am going to solve this relation, I will get in terms of sinc function, and that sinc function is a representation of a signal, rectangular pulse. So I will expand this. So this is ak is equals to a divided by j. It is 2 pi by ts. Omega naught is replaced k into ts. Okay. E to the power plus j omega naught k ts divided by 2 minus e to the power minus omega naught k ts by 2. So this ts get cancelled out. You take this j to inside. So it is a divided by pi k e to the power omega naught is 2 pi by ts. So here I will get pi j k e to the power minus j pi k. Okay, divided by 2j, because this 2j we have took inside. Now this is quite similar to your sine function. Okay, so here I will write a divided by pi k So it is A divided by pi k sine of pi k. Okay, because this k and ts have eliminated, and the k value is minus infinite to infinite, that I have substituted, and the integration we have done. So your ak coefficient is this much. Okay. Okay. So this is the constant coefficient if your limitation is this ts and minus ts by 2. For example, if this limit is not exactly as ts, if it is only t, so in this case, in place of this value, it is minus t by t if it is time period is there, if the limitation is ts by 2 less than t less than ts by 2. Okay, here we have considered that time period is minus ts by 2. So the sinc function is sine of this much is called as a sinc of pi k, like this, because sine theta by theta is sinc theta. So this is the value, for which case if the limitation is minus ts by 2 to ts by 2. But practical case it won't happen. Let us consider the time period. T lies between minus t by 2 to plus t by 2. So if this is the limitation, then your constant coefficient, it is a divided by j2 pi k. This ts get cancelled out. In this, it is e to the power plus omega naught is replaced by 2 pi by ts k t by 2 minus e to the power minus j 2 pi by ts k and t by 2. Done. So these two get cancelled out. These two get cancelled out. If the limitation is minus t by 2 to plus t by 2, it is not the sampling time period limitation. Okay. In that case, it is a divided by 2 pi k. It is e to the power j pi k capital T by ds minus e to the power minus j pi k t by ds. Then take this j, do j inside, you will get your sine function. Okay. So let me write. So our constant coefficient is a divided by pi k and e to the power j pi k t by ts minus e to the power minus j pi k t by ts whole divided by 2j. Now this is called as the sine theta. It is pi k. So sine theta means pi k t divided by ts. Done. Now here pi ts, this is the extra factor. You need to form in terms of sinc function. So what I will do? I will multiply and divide t by ts, here also t by ts, whole into sine of pi k t by ts. Now this pi k t by ts is same. So this whole part you can consider as sinc function. So it is a t by ts. It is sinc of pi k t into fs. Like this I can write. This ts I have to upper state, so it becomes fs. So here also I can write A into Fs into capital T sinc of pi k T into Fs. This is my constant coefficient. So this is the constant coefficient if the limitations, what is the time period for a pulse, if it is not same for the sampling time period. If it is same for sampling time period, then you can extract the constant coefficient as A divided by pi k sine of pi k, that is A sine sinc of pi k. But if it is not time period Ts, then this will be our constant coefficient for practical case. Okay, so let us consider this as A. Now we need to determine the function. Which function? The pulse function. We need to substitute this value. Then we will multiply with our m of t and we will take the Fourier transform of it. So let us see. So now C of t is equals to summation minus infinite to infinite a k e to the power plus j omega naught k into t. Done. In place of a k, substitute this value. If I am substituting a fs into t, summation k is equals to minus infinite to infinite, then sinc of pi k t fs e to the power j omega naught k into small t. So this is my function. So it is sine of pi theta divided by pi theta is sin theta. Okay, so here pi I will not include. So it is sinc of kt into fs. So it is sinc of kt into fs. This is the property for your sinc function. Okay. So we not to include these pi terms. So here we need to represent sinc of kt into fs. So sinc of kt into fs e to the power j omega naught a fs into t. So now this is the relation. Now next we are multiplying s of t is equals to c of t into m of t. M of t is our message component, so that we need to multiply. So if I multiply, I will get a fs into t summation a is equals to minus infinite to infinite. It is sinc of kf ts, okay, e to the power j omega naught k into t into m of t. Done. So this is the representation. Now here the sinc function is independent of this particular part. So here we can see m of t. Okay. So this is my s of t. Now I need to analyze this one in terms of frequency spectrum. I need to identify the frequency positions, sample positions. So what I will do, I will take Fourier transform for above equation. So s of t will become s of f. This is a multiplication property. If you take this multiplication property in terms of Fourier transform, it will become in terms of convolution. Okay? Or if you take convolution Fourier transform, it will become multiplication of individual transformation. But here it is multiplied, so that means the resultant of the Fourier transform will be the convolution. Okay. So what are the constant? Let me write first A Fs into t. Then convolution means summation n is equals to minus infinite to infinite. Then this is the constant function sine of k Fs into Ts. You can see m of t will become m of f or m of omega, and there is a frequency shifting with omega naught k into Ts. M of omega is frequency shifted to omega naught into k. Okay, so if it is satisfying the convolution property, here I can write m of f minus n fs. Okay, what is fs? Fs is nothing but omega naught, which is omega s. So here I have represented the whole function in terms of f. So here I am writing in terms of f. You can write in terms of omega, but one thing, you need to divide 1 by t naught to it. If you are writing in terms of frequency or f, you need to identify the constant factor. This is minus infinite to infinite. Sine of k f t, that is a constant function, and this is called as your time shifting property. So time shifting property of it, convolution is m of f minus n fs. So this is the resultant spectrum what we will get after natural sampling. Now we will see how to represent this. Here the amplitude is not uniform for different position of omega s. If n is 1, then what is the value? If n is 2, then what is the value? All different amplitude will be with respect to omega s, with respect to omega 2s, with respect to 3 omega s, with respect to 4 omega s. Let's see. So this is my s of f. So when I am substituting n is equals to 0, so it will become as n of m of f. That's it. And rest as it is. So it is a sinc function. So I will get the maximum amplitude when it is omega m minus omega m. Okay. Next, if n is positive, if n is 1, f minus fs. That means at fs we will get one form, that is fs plus fm, fs minus f. Okay, amplitude decreases, sinc function. Then again for 2fs, if n is equals to 2, positive. Now this is the amplitude, because it is a sinc function, means if the number of values increases, it means amplitude will decrease. Similarly, for left hand side also, you can represent, if n is minus 1, you will get f plus fs. So this is minus fs plus fm minus fs minus f. Then this is minus 2fs. So this is minus 2fs plus fm, and this is minus 2fs minus f. Okay, and here you can see that amplitudes are changed, and it follows the sinc function. Sinc function means this is the sinc function s of omega having amplitude 1. This is what if the rectangular pulse rect of t. Here rectangular pulse is our having a certain amplitude. What we have considered? This is the rectangular pulse having amplitude a, t by 2 minus t by 2. This is c of t. When you convert this one into frequency domain or in frequency Fourier transform of this pulse, it will become as a sinc function, this one, like this. So as you can see, the amplitude of the consecutive position of Fs decreases. So that means it will, all the spectrum will lie within this sinc pulse, because here we have considered that C of t is a rectangular pulse and this is our sinc function. It is satisfied because this sinc function is there. It is a sinc of kf ts m of f minus fs. In instantaneous sampling, we are getting all the spectrums of individual position of fs, 2fs and all are having the uniform amplitude. But in the natural sampling, the amplitude differs because rectangular pulses we are using and which vary with respect to the modulating signal or continuous time signal. So this is the mathematical representation and this is the frequency spectrum for flat top sample signal. Frequency spectrum for natural sample signal. Natural sample signal. Okay, so this is the difference. Next we will discuss about the flat top sampling. Okay, so this is the last part of today's discussion, that is called flat top sample. The flat top sample spectrum is similar to your natural sampling spectrum, which is also contains of same sinc function, because here also we are going to represent the sample signal in terms of rectangular function, okay, and whose top of the sample will be flat. It depends upon the circuit. We will discuss that one while discussing at the end of the session. So first, how to get the flat top sample signal. The basic technique is, first the instantaneous sampling will happen and then a small rectangular pulse is going to convolute with respect to that instantaneous sample signal. Then we can get the top of the sample will remain constant. Let's see. So first, let us consider the modulating signal or continuous time signal. Then to this, impulse train C of t is equals to minus infinite to infinite del of t minus nts. Okay, so these are the pulses. Okay, amplitude is 1 for different time period t. This is ts, this is 2ts, this is 3ts, this is 4ts, this is 5ts, like this. Minus ts, minus 2ts, left hand side. This is plus. Okay. So when you multiply these two are given to the multiplier, we get the instantaneous sample signal. So instantaneous sample signal means it will look like this. So if you join this modulating signal, so here I will write S of, this is Ts, 2Ts, 3Ts, dot. So this is instantaneous sample. Now to this instantaneous sample, if a rectangular pulse, this is the rectangular pulse, rect of top, let us consider. It is amplitude is 1 and time period is t. Okay. Now when you multiply this rectangular pulse to each and every pulses, now this again we are using one more multiplier in which S of t and the rect of tau, if we are multiplying, then the output for this particular position, when you multiply this particular pulse, you will get first pulse. With what? The sample whose top is flat. Similarly, another sample whose top is flat. Similarly, another sample whose top is flat, corresponding to this position. Similarly, corresponding to this position, corresponding to this position. Similarly for this, similarly for this. Okay. So here, whatever the sample s of t we are getting, this is called as a sample signal. Done. But what is the difference between natural sampling and flat top sampling? In natural sampling, the amplitude of the sample, it remains, some parabolic changes will be there. It follows the same content what is our modulating signal had. But in flat top sample, first instantaneous sampling has been done, then you multiply this rectangular function to the each and every position, you will get your sample as a flat top. So the sample signal having flat top positions or nature. Now we need to analyze so these all are sample signal. Like this. So this is your t, this is your 0. So this is called as your flat top sample signal. Now we will continue with mathematical analysis. Mathematical analysis. Okay. So as you can see, I have written few steps with respect to this flat top sample. For mathematical analysis, we need to model it. Okay. So here it is a simplification resultant of our natural flat top sample signal. So here what I have done, m of t is multiplied with the carrier power c of t, which is a pulse train, what we have considered here. That is minus infinite to infinite del of t minus nts. Okay. So if you multiply these two, you will get your instantaneous sample. So this s of t I have written m suffix del of t. Done. So it is m suffix del of t. Next, it is entering to a particular filter. Here it is nothing but a multiply, in which this rectangular function is multiplied and we are getting. It is a simplification. But practical case, it is nothing but a filter. The filter is having a certain response h of t. Depend upon this response, we will get our flat top sample signal. So s of t is the flat top sample signal. Okay, flat top sample signal. Now what it is? M del of t convolution with h of t. Done. Now first of all, we need to design this h of t so that the rectangular function will multiply position to position with respect to the instantaneous sample signal. Okay. Now what is the rectangular function we have considered? It is rectangular function we have considered that for time period t, amplitude is 1, the rect of tau. That rect of tau, this tau is nothing but t by t, small t by t minus half. How this particular thing happens? Let's see here. So filter response is h of t. Now rectangular function we are considering, that is rect of tau. So h of t minus 1 minus half to half, because the total duration is 1 we have considered, amplitude is also 1. So it is 1 minus half to half. It can be written as rect of t by t. T is the pulse width, t is the total time period. Okay. So rect of t by t is equals to 1. When it is 1, when it is lies between half to minus half. So it is half to minus half. Okay. Now we need to for total time period. So what I will do? I will shift this pulse to right hand side. So if I am shifting this pulse to right hand side by half, that means it can be called as a delay. So this t by t is delayed by half. So what I will write? Rect of t by t minus half. So that I have written rect of t by t minus half. So it is delayed. So if it is delayed, that means the resultant will look like this. Amplitude is 1. The total pulse is shifted to right hand side. The total time period is 1. So what is the function? Rect of t by t minus half, which is equals to 1 for the time period, minus half to half, but the time period is what? T by t minus half. It is delayed. Okay. Now this is my rectangular function. This is the response of h of t. So h of t is equals to this. I will substitute here. M of t I have determined with respect to the convolution of multiplication of this modulating signal and this pulse chain. I will take individually Fourier transform, and then as per the relation S of t, if I will write like this, S of f, m del of f, okay, convolution will become multiplication and h of f. So this relation I need to identify. So what I will do? Step by step I will take the transformation and then I will multiply those two transform value to determine S of f. Okay? Okay. So S of t we need to calculate with the instantaneous sample signal and the filter response. Okay? Now instantaneous sample signal is m del of t, and what is the filter response? Rect of t by t minus half, that we have derived. Okay. Next, since it is a continuous function, you can't take summation convolution. You need to take line convolution. Okay. So it is minus infinite to infinite, or you can say it is called integral convolution for continuous function. So it is minus infinite to infinite m del of tau h of t minus tau into d tau. Now whatever the thing we have obtained with respect to rectangular function, we need to substitute here. Okay. So first, this is the m del of tau. What is m del of tau? It is nothing but convolution of the sample signal with respect to the pulse train. So it is minus infinite to infinite m of nts del of t minus nts. Okay. And what is h of t minus tau? H of t minus tau as it is, this is nothing but the output of instantaneous sample signal. What we have determined with instantaneous in previous class. Okay, that I have written directly. Next, take this integral inside and this summation part take outside. Summation of minus infinite to infinite m of nts, because this function will come with respect to this integration. So it is summation minus infinite to infinite m of nts minus integration to plus integration del of t minus nts h of t minus tau into d tau. Now whenever this impulse function shifted position multiplied with another function, the function will also become as a shifting function. So it will come under as a time shifting property. So this del of t is multiplied to any of the function resulted in that function. Similarly, del of t minus nt, if I will multiply to that particular signal, then it get also shifted to the nt. So it is del of t minus nts h into t minus del tau into d tau, which I can write in this sort of form. So this h of t minus tau is shifted to t minus nts, because here del is shifted to nts. Okay. So here m of nts into h of t minus nts. Now this is what? This is nothing but the convolution part. This is what? This is m del of t and this is h of t. So now m del of t is convolution with h of t. It is satisfied. Take the Fourier transform. You will get m del of f into h of f. So now we need to calculate individual functions. So m del of f, this already we have determined while discussing our instantaneous sampling, that is fs minus infinite to infinite m of f minus n fs, that is m. Okay. First, second, h of f. How to determine h of f? Minus infinite to infinite h of t into the power minus j omega t into dt, that is our relation. But here the rectangular function lies from 0 to 1 and having the amplitude 1. 0 to t, amplitude 1. So 0 to t, amplitude is 1 e to the power minus j 2 pi ft. It is a simple integration. Solve it. You need to represent this whole expression in terms of sync. So as you can see, 1 by minus j 2 pi f, it will come outside. When you substitute 0, it will become 1. When you substitute t, it will become minus. So it is 1 minus this much. Done. Now if you take this e to the power minus j 2 pi ft as a common, this sort of relation will come into picture. This 2j take inside, e to the power j theta minus e to the power minus j theta divided by 2j will become as a sin theta, sin pi ft divided by pi f e to the power minus j 2 pi. This equation is similar to our natural sampling. Here also sync function is there. So how to determine sync function? We need to multiply t to it. So t is multiplied here and above, and take this one as a sync function. So this pi ft and this combination division will become as a sync ft. And what is the amplitude? T into e to the power minus j pi ft. Now h of f is known, m del of f is known. Now you need to multiply this one with respect to this to determine s of f. Okay. So m del of f, h del of f substituted. So this is our m del of f and this is our h of f. When these two are multiplied, again it will form in terms of sync function. That means the spectrum for the natural sampling and flat top sampling are quite similar, because both the cases it is having the sampling sync function, and that too its amplitude is also valid. You can see here amplitude is valid. So when you substitute n is equals to 0, you will get the maximum amplitude. When you substitute n is equals to plus 1 minus 1, according to that, the less amount of energy will be distributed on the relevant spectrum. So this is the basic representation of the mathematical analysis of flat top sample signal. Next class we will discuss how the sample signals are generated, flat top sample. Okay. So for this session, thank you all.